So let's look at a visual trace of our first implementation of find it. Let's take the example ample as we had earlier with part, and let's make text a little bit more interesting where there is a lot of partial matches. So for example, we have when we have a match here A, but then the next character is not M, and then you have a partial match again over here and then over here and so forth. So a lot of failing partial matches. So let's look at how our implementation actually goes through the text and part, and where it spends most of its time. So first we go through E, X, they are of no interest. Then we look at this letter A, which matches the first character of part A, and hence we try to match the subsequent characters. But the very next character is not M, but it is another A. So now we know that though the first character matched, we actually do not have ample starting at position 2 in text. So what we do, we start our search from position 3 instead, because we already know we don't have ample starting at position 0, 1 or 2. So starting at the very next position 3 is a fair idea. And then we start to examine the characters from the third one, and we see that okay, the third character in text actually matches with the first character in part A again. And then we start to build a partial match. We start to examine the subsequent characters. We have A, we have M, but the fifth character, which we expected to be P, is not P, but it is A instead. So we break our search, and what do? We know that we could not find ample starting at position 3 over here. So we actually then start at position 4. Now, but we have already examined the character at position 4. It is not the first character of part A, but it is M. But still we somehow have not kept track of that piece of information. So we'll have to go back to M only to find that it is not A. And then we step to the next character at position 5, which is an A, which matches the first character of part. And then we say, okay, we have a match starting at position 5. Let's see what happens next. Let's examine the subsequent characters. So everything goes fine till A, M, P, but when we expect L at position 8, we instead find character A instead. So we give up on our search over there at character at position 8, and what do? We found that we do not have a partial match. I mean, we do not have a match for the text ample starting at position 5, so we start at position 6 instead. So that's very robust. However, we again are missing out on the information which we have already skimmed through. I mean, as we scanned through as we did our previous iteration, we know that we have M and P here, but not A. But still, we do not keep track of it, and hence we start at position 6. We again check if position 6 is A. We see that's not the case. We go to position 7. We check if that's A. That's not the case, and then we hit upon A at position 8, and then we say, okay, are we going to have our match starting at position 8? And then we set off our we start to match the subsequent characters of part in text, which goes on fine for the subsequent characters A, M, P, L. So now we have one extra character, but then so it's almost there, but when we expect the last character to be E, we instead get an A, and then that ruins it all. So what do we do? You know the drill. We go back to position 9, and then we again match, we try to match, or we compare, if we compare position 9, position 10, position 11 with the first character of part A, though we already knew that they were not. I mean, we knew, but we never recorded it, so we don't have a memory of that. So we just forgot. So we are just going back, and then in a robust way, checking from one position after position 8. And finally, we hit upon A at position 12, and then we have a complete match of the character ample over here. So this backtracking seems to be where we can have some improvement in efficiency, because we are already examining some characters, but then we are just not keeping track of the characters that we have examined in text. So that's food for thought that we can keep in our mind to try and improve our string finding algorithm. So what else can we do to actually improve our execution for this particular example? If we just just look at it, it doesn't hurt, but we can just still try. So one way is, in a straightforward implementation, our logic was, whenever we have a partial match that fails, like for example here, we go back to a position that is one higher than the start of that particular partial match. So we had a partial match beginning at position 5, and if that fails for some reason, then we start at position 6. Now instead of looking at the start position of the partial match, what if we look at the end position of the partial match? So for example, if I know that a partial match has failed at position 3, why not start right at position 3? Because I already know that this logic could be wrong, of course, but just for the sake of consideration. So just to make some kind of progress, even though it may not be correct. So what if we say that instead of considering the starting position of the partial match, what if I consider the ending position of a failed partial match? So I have a failed partial match at position 3. Why not I start my search right from there instead of going back? Now that doesn't make any difference here in this case, because even our straightforward implementation is starting right there at position 3. And now we go to position 5, where we have a partial match that fails. So it doesn't match completely to part, it only matches till A and M. So what if we start right at that position? Now that doesn't seem to hurt much, because the starting point here, as we see, it was anyway at position 5. So we save ourselves this extra comparison of M with A that we were doing in our straightforward implementation. And then when we find a failure, a failed partial match that ends at position 8, instead of going back to position 6, why not just start at position 8 instead? And if we look at our straightforward implementation, it saves us these two extra comparisons that we were doing at position 6 and position 7. So this seems to be an idea that works well for the example data that we have considered here. So, but then we have to supplement it. We have to see if it's generic enough, I mean, if it is general enough, and if it's a solution that we would like to consider. So, and if we look at the steps over here, there is no backtracking whatsoever, and then it reduces our worst case runtime complexity from n times m to just n. So that is very impressive and worth considering. So let's try to implement this version of the solution and see how it fares with our current example data, and also with then we'll try to change the data and see whether it's good enough or not. So let's now implement the optimized version of the solution that we sketched out. Let's begin by renaming our existing function, the straightforward function, as find it brute force, because obviously it's not doing anything interesting. It works well, but it doesn't seem to be an intelligent implementation, so we call it a brute force version of find it. And then let's copy this over and start to implement our optimized version. We don't need all of this here, so we keep the brute force function just for comparison, because we know this is a correct implementation, so we can just compare the correctness of the future versions of find it that we implement, and that's the reason we still have it and we have not thrown it away. So in our improvised solution, what do? We define indexes into text as t and into part as p, and while they are within bounds, so t is less than n and p is less than m, we check if text at t equals the character at position p in the string part. If it is so, we have a running match that is going on. So all we do is step the indexes. Oops. So t goes up by 1 and p goes up by 1. Now if p is greater than 0 but we do not have a match, which means we had a partial match going up till p minus 1, but at position p the characters do not really match. So what do? As per our sketched optimized algorithm, we reset p to 0, because we start at the ending point of our failed partial match. So t remains the same and p rolls back to 0. Now this is something which we may want to reconsider, whether what happens to p. Does p need to be reset to 0, or can it this is still not very clearly defined. When we are trying to code it out, it looks like we have not covered well for this case. What should we do with the index into the part? How far back should we take it, or can it go somewhere greater than 0 and less than p? Don't know yet, but let's leave in the comment over there. And now the else of these two blocks indicates that we do not have a partial match going on, and even the current character in text does not match the first character in part. So in that case, we can just simply go t++. So we just go to the next character in text to try and check if that one matches the first character in part. So having coded this, once we are out of this loop, if the index into the P has gone over the index into the part has gone over its size, it indicates that we have matched all the characters of part successfully. So we can just return the index into text less than m characters, that is the size of the part. So if when we have matched the whole of part, if we are at position t, then we would have been at position t minus m when we have matched the first character in part. So we return t minus m over there. Let's see if this works or if I've made any mistakes in the implementation. So our input is still at, let's check, it's at ample and example. So let's run this. Okay, I think we forgot to output the result of find it optimized. So let's change it here from brute force to optimized and over here to optimized. Now let's run this again, and then it seems to work. So we seem to get the same result. Now we can replace it with the other longer example that we had, exam and amp and amp and amp and ample, and then let's see what happens. That seems to work well too. Let's give let's give a negative test case. So we have a string that doesn't match, so both of them should return -1, and that is correct. Now let's try to play around with this input a little bit more. What if the part, the string of interest for us is the word AMAP, without the space, of course, AMAP. Let's take it that way. And we have text exam app. So we have an exam app, I don't know, whatever, an application that helps you with your exams. And then we want to look if it contains this word AMAP. And obviously by visual inspection we can see it does over there, right? So let's execute this, and that seems to work fine too. Now let's try to put in a bit of a repetition here like the last time. So we have exam app, instead we say exam app, and see what happens. So we should be having a partial match here. So we have one partial match here, AMA, but then it fails there at M because we expect a P. Now a robust implementation, brute force implementation, gives out the correct result. Index 4, if we count 0, 1, 2, 3, 4. This is where at index 4 is where we have AMAP in exam app. However, our highly optimized, intelligent, not thought through and hasty implementation fails. So now we have to get back to the drawing board and stop being lazy here. So we have a problem with the optimized implementation, a minor problem. What is that? We have incorrect behavior. Obviously, I was kidding when I said minor problem. Yeah, what good is an implementation if it's not correct? It can be as much fast as one can imagine, but it's of no use. So our solution, it seemed to work for some test cases, but not all. Now, this is just about the time when we should stop fiddling around with limited thought and then ideally just take a step back and think of the problem, uh, establish a global invariant. And if you wonder what a global invariant is, it is a condition or property in the problem domain that never changes while you solve your problem. So, and that is if you are solving it right. So that actually kind of helps you develop the solution in a more robust way. So what were we not sure of in our linear time solution? It's in this else if block where when we had a failed partial match, we really didn't know what to do with the the index into part. So we had it greater than 0, but we didn't know what to do with it. So we just set it back to 0, and I think that is that was the problem in the implementation. So that's where we actually need to work at. Now, if we look a bit more closely into the possibilities that there can be when we hit the situation where we have a failed partial match, uh, at the condition where we have the failed partial match, if we just draw a border here as depicted here, we are at index t in text and at index p in part, and the characters at those two indices don't match with each other, but p characters behind those indices match with each other in both the part and text. So if we look at this pictorially, we can probably visualize that there there may be some character in part at some position p prime. Let's consider this position p prime, which actually matches with the character at position t in text. So, and then if this is p prime, so we have so many characters in part that match with the characters in text from index t uh, backwards. So we have a new partial match here. Instead of going all the way back to 0 over there, we could actually set it to this new index. And then there could also be multiple such indices. So I try to draw another one right there, which is over there. So now that has a match of so much. We just recreate the parallelogram. Yes. So now we have, I mean, this is a possibility. It's not like it's always going to happen. There is a possibility that we have more than one partial matches behind the position P that can actually match up to the same number of characters behind the position T. And then if we choose the longest such partial match that leads up all the way to position T inclusive of T, then we seem to be making some progress, and our solution will probably be correct. So our global invariant is something that ensures this transition of index in the string part from P to P prime whenever a partial match fails. So if we somehow ensure that whenever a partial match fails, we correctly switch the index into the part from P to the appropriate P prime, then we can use our existing solution and make it behave correctly. So these pictures just reiterate what we have discussed a few minutes ago, but we also instead we make it explicit that whenever we get into the else if block where we have a failed partial match, instead of setting p to 0, we assign p the value of this function next p of t, which magically fetches the new and correct value of p prime, and then we assume that next of t satisfies this particular condition. We just pictorially we looked at it a minute back, so but descriptively it will be something like this. So I just don't want to read it out, but I'll just pause for a moment there. Now this is all good. It can be clear or it can be confusing depending on how I said these words actually. So, but if it's clear, I think this is just enough to take off and implement the or discover the KMP algorithm. But if not, we can just park this idea here at the back of our mind. It will sit there like a vague idea. Then we can continue to develop our solution in a more intuitive and iterative way.